Just give me 5 more minutes. 5 minutes. Can you see the notes? Okay. I don't know, my system is running slow for some reason. Trying to fix it. Okay. I'm moving to another system. It takes some more time. Okay, sorry for the delay. Okay, sorry for the delay. And okay, hope notes are visible to you. Okay, so we'll continue with our discussion on greedy algorithms. So far, we have been looking at scheduling algorithms, and now we'll move on to some graph theoretic stuff. Right? So the first problem we want to look at is minimum spanning tree.
Sir,
Oh, yeah,
notes are not visible.
nodes are not visible.
It's blank, black.
Okay. Can you see them now?
Yes, sir, it's visible.
Okay. Yeah, so yeah, we will look at some graph theoretic applications of greedy paradigm. And first one we will look at is minimum span, right? So all of you know the problem. It is you are given a graph with a set of vertices and set of edges. It's a connected graph. You could also consider disconnected, but then this won't be a tree, it will be a forest. So each edge has a cost associated with it. Let's say there's an edge. So edge connects two vertices. Let's say some ij, and each of such edges has w of ij associated. Okay. So whatever output is going to be, it is find a subset of edges such that this graph is connected. Right? So what is such a subgraph that we want to find? And obviously we want that the total cost of edges is the smallest. So you could think of it as you have some business, let's say, which is running in many cities. And there is a cost, and you have various offices in various cities. And there is a cost behind connecting some two offices. Okay? And obviously you want to minimize that cost, but you want to also ensure that all the offices are connected. So the cost is essentially the cost of connecting two offices with some telephone lines. Okay. So yeah, total cost of edge is smallest and want to find the minimum spanning tree. So tell me some greedy strategy. Sort the edges by their weights. Okay. Is that enough? You also have to ensure that you don't create any cycles because you don't want two different paths from one vertex to another. Just one path is sufficient. Okay, so one strategy is we can select the minimum cost edge, right? Then what do? You select the second minimum, third minimum. But there is a danger in this that you might create some cycles. So how do you ensure that no cycle is created? How do you check? Go to the input. Okay. Yeah, this is the input. You have a connected graph and each edge has a cost associated. If a node is already visited, then okay, yeah, that's sort of the idea. So this is one approach, and I will present to you four different approaches for solving this problem. And then obviously you have to check for correctness and running time. Okay, so what are these approaches? So here is one sample graph. You have the set of vertices from A to J, right? You have all these edges and those which are connected in red, they are your spanning tree edges, okay? And you check whether the edges in red, they don't create any cycle. And then you just sum up the weights of these edges, okay? So here is one greedy approach for minimum spanning tree, which is that the tree is initially empty, there are no edges. This the tree you are trying to connect. And while E is not empty, we choose some edge, and if the edge E satisfies the particular condition, we add this edge to the spanning tree. Okay, and then finally return the set T. So, yeah, and what is this condition? That we don't want to create any cycles. We say that the graph corresponding to GT, where V is the set of vertices, T is the set of edges, and you added these edges according to whether they create a cycle or not. This is our minimum span. Okay. So there are two questions now. Uh, we'll check if the connect should not be already connected to each other. Yeah. So what data structure are we going to use? Linked list. Okay. That is one approach. More efficient than linked list. In EPR, you do that. Map. Okay. So there are some problems with various approaches. Actually, these are not the optimal data structure which you are going to use. All your answers are correct, but there is even better data structure than all of these, which is called Fibonacci D. Okay, but before going into data structures, let's just answer these two questions, which is in which order should edges be processed? That's exactly what one of you suggested. We'll sort the edges in increasing order of their weight, and that is the order we should be processing the edges. And when should we add edges to the span? That is the step when we are going to check for cycle. Okay. So there were many ideas that uh, we will check whether the two nodes are connected or not. And if they are connected, we don't have to add that edge. And if they are not, then we can safely add that particular edge. Okay, so let's see our first algorithm. It is known as the Kruskal's algorithm. Here is it. Uh, you are given a graph, a set of vertices, set of edges, and W is the weight assignment to this edge. Right? Initially, your tree is empty. Sort the edges in non-decreasing order. That is what the sorting step will give you. And while the edge set is not empty, we choose edge. If he does not form a cycle with edges empty, just add that edge and return the set. We'll look at one example. So here is one example. You took the minimum weightage 2, no cycle is created, so that is fine. And the next minimum is 5, that also you can add. 7, 8, 9, 10, then 12, then 14. So far we haven't created any cycles. But when you add 15, there is a problem because it creates a cycle with 5 Similarly, 18, there is a problem. Creates a cycle with 7 9. 21 also there is another problem. 25 there is a problem. 28 there is a problem. So you don't add all these edges and this is what you get. The edges in green, those are your edges, the spanning. And you just sum up the weights of the edges in green and return that weight as the weight of the minimum spanning. So we still have to answer how we will check for the cycles in Kruskal's algorithm, and that is usually done by a special data structure which none of you mentioned, which is called the union find data structure. Okay, so do you know what is union find data structure? No. Okay. So here the so I assume that this would have been done in data structure, but it's okay. Uh, so the idea is the same. Whenever you add an edge into the spanning tree, you check for the set of edges. So initially, each vertex is its own connected component. Okay? So you construct a set which just consists of one vertex. So here I'll construct a set consisting of A, another set consisting of B, C, D, E, F, G, H, I, J. Okay? And whenever you add an edge between two vertices, now this set consisting I and the set consisting J, you will take the union of those two. Okay? I comma J. Right? Similarly, if now I and J, these are one vertex. These are not two different vertices. So essentially you contract this particular edge. Okay? Because once we add an edge, we want to know what is the next minimum edge you can add. Correct? And for that, let's say that ij belongs to my minimum spanning tree. Okay. Now I want a smaller graph whose such that if I compute the minimum spanning tree on that smaller graph, it will give me the entire minimum spanning tree of the bigger graph. So what is the spanning tree of the bigger graph? It will be this edge ij union with the minimum spanning tree in the smaller graph. Right? So how will you find a smaller graph? That's the first question. So people have tried different ideas. One is you delete the edge ij from the graph. Okay. But unfortunately, deletion doesn't work because it could be that the residual minimum spanning tree that doesn't create a cycle, but along with this edge ij, it creates a cycle. So we cannot just delete off this edge. And so what we do it, we contract this edge. So there is a certain graph contraction operation you are not familiar with. You just merge these two vertices into two. So this edge doesn't exist. But now these two vertices are merged into one vertex, which is called I comma j. Okay. So that's how you merge these sets together. So when if you added this edge ij, your graph will have a new vertex or new set I comma j. Okay. When you added this particular edge, now there will be a new set I j comma h. Okay. And when you added this particular edge, there will be a new set I j h comma f. So you create such sets everywhere. And what is the use of this set? Right? So whenever you are adding a new edge which is creating a cycle, you just check whether those two vertices are in the same set. Okay? That's why it's called union find data structure, because one thing is it is computing the union of all these sets, and whenever a new edge is coming, it checks whether they are both in the same set or not. Okay? So that's what this idea behind the cluster algorithm. And yeah, any questions so far? Okay, there are none. We'll move on to the next algorithm, which is essentially using the correspondence between cuts and cycles. Graph cuts. What is a cut? You just partition the graph into two different, partition the set of vertices into two different sets. Okay, that's the main idea behind the Prim's algorithm. And that's what we are going to see. So if you are familiar with some graph theory, what are some examples of graphs which don't have any cycles? Okay, so one example is bipartite graph. It doesn't have any odd cycle, but it could have even cycles. So what's the idea of a bipartite graph is that you partition the vertices into two different sets such that all edges are going from one set to another set, right? That's what is called a bipartite. And why can't it have any odd cycles? It's because in every step you are making a transition from one step to another. So if you want to make a return to the same set, you will have to make an even number of steps. In odd number of steps, you will just move across to the other side, right? So that is why it doesn't have any odd cycles. And the same idea we want to use, which is this Prim's algorithm. So what his idea was, you take the minimum weightage going across any cut. And that edge should always be contained in span. So can you see why? So here we have a cut of these vertices. These are in one set. These vertices, they are in another set. And some edges are going across the cut. Okay. And what he said was that if you take the minimum weightage going across the cut, that should definitely be contained in the minimum span. Sorry, anybody said something? Okay, so this is the main idea behind Prim's algorithm. Initially, your spanning tree T is empty. This set X will contain some vertex S. Okay. So, what is the most trivial partition? Contain X in one set, and all the other vertex go to the other set, right? And while there is an edge which is going from X to outside X, you look at the minimum cost edge. So in this case, there was just one vertex S. So we are looking at the minimum weight edge incident with S. And these sets keep on growing. So while there is an edge with U belonging to X and D does not belong to X, you take the minimum cost edge. And you add that particular vertex in the set and this edge in T. Finally, return the set. So let's see how this algorithm works. So in fact, you could start with any particular vertex, but let's say we are starting with this vertex F. Okay. So what is the first edge you will pick? Its weight is 2. It is the so initially we'll pick this vertex F. So F is in one set and all the other vertices are in the other set. Okay. So what is the minimum cost uh, edge which is going from one set to other set? It is this edge. That's weight 2. Okay. So now you get a new partition into various sets. So this edge has been added and you have F and D now and all the other vertices are in the other set. So what is the minimum cost edge going from F and D, F of D to the other ones? It's this edge, 7. Okay. So you add that edge and now you have F, D and H in your set. Then the third edge is uh, this one. Okay. Then you added this J also in your set. So F, D, H, J are in one set and all the others are in the other set. What is the next one? It's fine. Okay. So because there was one thing in the initial algorithm where you are just taking the sorted order of the edges, it's because you don't have any reason to believe that the minimum cost edge should always be contained in a minimum span, right? Because it might be possible that you pick the minimum cost edge and it runs into a cycle, and you could have picked some other small weight edges and ensure that there is no cycle. Okay. So in fact, that needs a formal proof why the minimum weightage should be contained in some spanning tree. May not be contained in all minimum spanning trees. Right? because there are many different spanning trees. Some of you might find something else. This is just one of them. There is no unique spanning tree, minimum spanning tree. So in fact, the original idea comes from this Prim's algorithm, which is that the minimum cost edge going across any cut that is always contained in some spanning tree. So any ideas how we can prove that? Why is the minimum cost edge going across any cut always contained in some spanning? So we'll go over this proof in detail, but let me just tell you what's the main idea. So the idea is that if you go across a cut, so you have partitioned the set of vertices into two different halves, and it may not be a half. There could be one vertex in one set and minus one vertex in the other set. But you understand what a partition is. And if you deleted this minimum weightage across this any cut, that spanning tree will break into two different trees, right? And instead, if you wanted to reconnect that thing, again you will have to introduce some other edge, which is connecting these two sets into partition. But since we have picked the minimum weightage, that edge will have strictly higher value. Okay? And that will lead to rise to a higher weight spanning. And that is the reason why we always pick the minimum weightage going across. Okay. That replacement edge always has to connect these two different sets. So that's the main idea behind Sprint's algorithm. And the third idea, which is often used in minimum spanning tree things, is it's called this reverse delete algorithm. Okay. So you go in the reverse order. Okay. So we sort the edges in decreasing order of their weights or non-increasing order of their weights. While E is not empty, E does not disconnect T, then remove E from T. Okay. So we picked all the edges in our spanning tree. We don't care, just pick all the edges. And obviously you will have to remove, there are lots of cycles being created, so certain edges uh, have to be removed from this tree. Okay, but what we do know is that if you remove E and the tree disconnects into two different parts, that means it is the only edge which is connecting those two different parts. Thus you have to include that in your minimum span tree. So that is why we use this simple property that if E does not disconnect T, then you remove E from T. Finally, just return this. So a very simple algorithm, and this is called reverse delete time. And first thing is, why did we choose the edges in decreasing order of clearance? The highest weightage first, then the next, and so on. You could pick any order, but what is the reason behind this specific order, decreasing order of the elements? And the reason is that we will show that the highest weight edge in any cycle that can never be a part of any spanning tree. So can you see that why the highest weight edge can never be a part of any spanning tree? For instance, here, initially we included all these edges in our spanning tree and we looked at the highest weight edge, 35. It is creating cycles many places. And why is this edge not a part of any spanning tree? So again, we have to use the same idea as we did in the previous case, is that which is by contradiction. So let's assume that we had some spanning tree with this edge, 35. Okay, you delete that edge, then the tree will break into two different parts, right? And because every edge in that tree is there because it is very important for that tree. Otherwise, the tree will break into two disconnected rows. There is a unique path between any pair of vertices in a tree. So once you delete this edge 35, it will break into two different parts. But now there is a cycle and there are lots of these edges. So there will at least be one of these edges which is reconnecting that tree together. Okay? And so we can always include that edge, reconnect the tree back and get a smaller minimum span. Okay? And that is why we do this algorithm works because we took the decreasing order of the weights. If the edge is creating some, if the removal of this edge is not disconnecting anything, then you safely remove it, and otherwise the thing works as it is. So this won't work for any other order. Let's say you say we sort the edges and consider the edges in that order. That's not going to. It strictly has to be in decreasing order. Okay. So here you can easily verify this example. 35 was creating some cycle, 32 was creating some cycle, 28 was creating some cycle, and we look at 27, that wasn't. So if you remove this 27 in the word edge, then we have a problem. Then we have some disconnections happening, and that's mean happening. Okay. Process the edges in this order and the algorithm works. And verify these things. And in fact, it's not that these three different ideas will give three different minimum span trees. Let's say we have this example, uh, we have this cycle, 2 to 2. So all of them can give the same thing. So you take anything, Kruskal, Prim's or reverse delete. Okay. So in Kruskal, what do? You sort these edges, pick the minimum weightage, and then just check for the cycles. Okay. If there is a conflict, you can consider these edges in lexicographic order. Okay. Just look at the sum of the words they are connecting. Will just work. And same thing will work for case of Prim's algorithm, E1, E2, 2, E3. Okay, some two of those edges, and the weight of the each of the minimum span trees is just 4. Okay. And the same thing works for reverse delete. You can verify these things. And there is a fourth idea, which was the first minimum span tree algorithm actually. Boruka's algorithm, but it's not much used nowadays. So what Boruka did was he considered this vertices as each vertex as one component. In fact, this idea led to Prim's algorithm later. So every vertex is a different connected component for you. Okay? And then he just took the minimum weightage, which is connecting these two. Okay? So it's a slightly inferior version of Prim's algorithm, but it was the first time. For each vertex V at the edge T whose weight is maximum overall, sorry, minimum overall edges incident. And he kept on constructing this tree. But he used a recursive call. Prim was more clever, but it's the same idea, actually, both are used. Prim was able to remove this recursion. His idea is more dynamic programming, which we'll later see in this course. So, any questions so far? So, how will Borugas proceed? Initially, every vertex is a single connected component, and he wants to pick the minimum weightage which are connecting two different connected components. Okay, so he started with A and looked at the minimum weightage which is connecting some other connected component. So initially A, B, C, D, E, F, G, all of these are just one connected component, and he connected A. So what is the minimum weightage incident to A? It is that 12 weightage. Okay. So that is for this first stage. What is the minimum weightage incident with B? That is again that 12 weightage. That's the second one. For C, it is uh, this edge, 27. Okay. For D, it is this edge, weight 2. What about E? It is this edge, weight 10. For F, again, it was the same thing. And for G, it is this edge, weight 9. And H, it is this edge. And you can just verify. And J, it just works. Okay. So this was the first step where he connected the minimum weightage incident with every vertex. He got this graph. Okay. And then he looked at, okay, so which components are now connected? So there are three main components here which are connected by these red edges. So there's one component in which both A, B and C, all of them are connected together. There is another component where D, F, G, H, all these are connected together. And there is another component where E, I, J, all these are connected together. So this is just a partial spanning tree which he has got, and he has connected the various components based on that. Okay. And then um, he finds the minimum weightage which are connecting these sets together. Because right now it's disconnected there are three different connected components. And then he found these two edges, B2F and H2J. Okay, H2J is weighted, this is of weight 40. And that's it. We have found the minimum spanning tree. Okay, so this is what podcast idea is. Then finally just compute the weights. Hopefully this is clear. And what do we learn from these algorithms? We have presented many MST algorithms and all of them rely on some basic properties of MST, which is the cut property and cycle property. So I've already told you about these things. Let's just quickly look at the possibilities. Just a second. Okay, so let's look at this correctness things and so all of them follow some basic properties, which is this cut property and cycle property. Oh, again, it's not responding. Okay, so all of them are following some this property, which is cut property and cycle property, and we always assume that edge costs are distinct, so that even in the same wet edges still works, but you need to assume something else. Okay, so we assume that all edges are distinct and that we always have some minimum weightage, maximum weightage. So this is what we call as a cut. We partition the set of vertices into two different sets and there are these edges going from one partition to other. This is what we call as the cut edges. What are edges in the cut? Edges having one endpoint in S, other endpoint in B minus S. These are the red colored edges. Okay. And as we already discussed, there are the edges, safe and unsafe edges. Is a safe edge if there is some partition of B to S and B minus S, and E is the unique minimum deposit edge going across. Okay. And this edge we said that it's always contained in some minimum span tree. Okay. Then there is something called unsafe edges. So this was the idea we used in Prim's algorithm. And there are some other things which we used in uh, unsafe edges. If there is some cycle C such that E is the unique maximum weight. Okay. Every cut identifies one safe edge because we assume that all the edge weights are distinct. So that's a unique minimum weightage and maximum weightage. Okay. You can easily verify that. So this was the cut property we saw that let S be any subset of vertices and E be the minimum weightage with one in D S and other in B minus S and every MST contains. Okay. By contradiction, let there be some MST which does not contain E. Assume that U is contained in S and B minus S. So there is a unique path in this spanning tree from U to V. And let's say B prime was these are the two vertices U to V, and B prime be the first vertex of this particular set. And it keeps on going, and U prime be the, so there is a path from U to U prime to B prime, B prime to B. So there will always be this replacement edge F. Okay. So if you delete E and insert this F, since E was the minimum weightage going across the cut, um, if you delete E and replace it with F, it is strictly going to give a larger weight span. That was the idea, right? And that's how we got this contradiction. Very easy. And we just use this fact that every tree contains n minus 1 edges. So you can always delete one edge and insert another edge. You are not allowed to insert two or more edges. Okay. And that's the thing. Basically, we prove the correctness of all these things. Pascal's, Premis, and Borucas. Okay, let's stop here. Any questions? Okay, if there are none, we'll stop this meeting now.